So basically, this is kind of like, envision you're in the court. You're in court, right? There's a trial. Yes? And there's a claim made. So-and-so did this. And they present evidence. And then the jury has to decide, and what decisions do they make?
Guilty, not guilty.
Guilty or not guilty, right? Do they ever say innocent? They do not. So that's an important thing to remember. They say guilty, then the evidence shows that they're guilty, or the evidence shows that they're not guilty. Okay? So a little bit of a difference between not guilty and innocent. Yes? Although it's very similar. So, in statistics, hypothesis is a claim. We're going to make a claim. Okay? About a property of a population. So, in particular, in this unit, in this section in particular, we're talking about proportions. Hypothesis test, another name for hypothesis test is test of significance. It's just the procedure we do to work through the claim of it. And it is said to be statistically significant if it isn't a reasonably likely outcome. Okay? So if we are, our claim, the test we claim ends up being not true, it's actually what makes it statistically significant. Okay? Okay, oh, it's wrong. All right, here we go. So, formal hypothesis test has 4 components. The first one, as is the case with confidence intervals, is we have to name the test and check the conditions. Okay? So the conditions look very, very similar to the ones we used yesterday. The only difference is that P that's there is not the sample proportion. So it's not what happened when I went out and did it. It's the claimed proportion. So we'll get to that, bless you, in a second. We'll get to that in a few minutes, but that P is just a slightly different number than the one that we used yesterday. But everything else about it is exactly the same conditions. Simple random sample, and P and N times 1 minus P has to be at least 10, and the size of the population is at least 10 times the size of the sample. So we just check our conditions. If it's good, we move on and we're happy. If it's bad, we move on and we're sad. Okay? All right. So first thing we need to do is state the hypotheses. So the null hypothesis, and we denote it H sub O, which we say O. Right? Say it very quietly. Is just the claim about it that's equal to some claim. The proportion is 25%, whatever it is. Okay, that's the hoe. All right. We test it directly. We make a decision to either reject the hoe or we fail to reject the hoe.
Don't accept the hoe.
We never, ever, ever, never, ever accept the hoe. Never. We never accept the hoe. It is never okay to accept the hoe. If you learn nothing else in this class, that's what you should learn. Okay? So it's just the same thing as saying guilty versus not guilty and guilty versus innocent. So if we said innocent, we'd be accepting the hoe. We don't accept the hoe. Try to teach you many, many values in this class. That's one of them. All right? The alternative hypothesis, which I typically denote H sub A, which is ha. So we got the ho, and we got the ha. And is the claim that it's somehow different. Usually involves some sort of inequality, like less than, greater than, not equal to. Okay. So that's the first thing we do. We state our null and alternative hypothesis. Few notes about them. Few things about those. We conduct the claim as if the parameter the hoe. So if P equals 0.25, I run the entire test assuming that that's a true statement. Okay? If I were to go out and I wanted to run a hypothesis test and I wanted to actually make some sort of comment at the end about my hypothesis test, if I wanted to be able to specifically say I did this thing or whatever, I want to word it in such a way that my claim is in the alternative hypothesis. Saying someone is guilty, rejecting the hoe, is the most, like the strongest thing you can do. Okay? Saying someone is not guilty, failing to reject it, is not nearly as strong. Okay? So we want to, if I were to actually write a hypothesis test, I'm going to write the sentence in such a way that it's going to go into the alternative hypothesis. So the original claim, it can be in the null hypothesis. I could claim that the proportion of freshmen is 25%. It could be in the alternative hypothesis. I could claim that the proportion of freshmen is greater than 25%. Or it might not really correspond to either. And that would be like the proportion of freshmen is at least 25%, because that's greater than or equal to. And it's not really going to be in either location. Okay? So the next thing we're going to do is compute the test statistic, critical value, p-value, sketch a graph. So the test statistic is my z-value. I'm going to take p hat. What's p hat?
Sample proportion.
Sample proportion. This p sub 0 is your hoe, whatever your claim proportion is. And notice that that's what comes down here for your p's. So this should look very similar to what we did yesterday. This is your standard deviation, standard error, okay? All right, critical region, or the rejection region, is the set of all values in the test statistic test statistic that cause us to reject the null hypothesis. So it's a shaded region. It's going to tell us at what point am I going to decide to reject. The significance level, alpha, that's a Greek letter for alpha, the fish, is the probability the test statistic will fall in the critical region when the null hypothesis is actually true. So it's the probability that I'm going to reject the null hypothesis. I'm going to say it's not true. I'm going to find them guilty when really I shouldn't have rejected it. Okay? So there's always a chance that I make the wrong decision. Yes? Hopefully that chance is very small. So this is what it looks like, the critical region. So if the significance level is 0.05 and it's one-tailed, my the amount that's shaded to the right of 0.05, that z-value is 1.645. Significance level 0.05. So any z-value, if I did that test statistic and let's say I got 2.2, it would be in here in the shaded region. That's going to tell me to reject the hypothesis. Yes?
If it's closer to the line, is that significant? Like if it's 1.6457 as opposed to 2, does that matter more? Or?
Well, not if the alpha is 0.05. It doesn't. It does. My probability of being wrong is more likely at 1.6457 than it is at 3.25.
Okay.
But that's why sometimes we change our significance level. It's not always 0.05. Sometimes it is less or more depending on how much we care whether we made the wrong decision.
Nice.
Like if it's something that's really important that if I made the wrong decision it could like kill somebody, then I'm going to make my alpha level really small, so I'm less likely to decide to reject. If it's something that's like it's not the end of the world if I'm wrong, I might make it even bigger to like 0.1. So somewhere between like 0.01 and 0.1 is pretty common as far as, but 0.05 is like, if they don't tell you, we typically use 0.05.
Thank you.
Yep. Good question. All right, so the p-value, this is really important that you understand this and actually can basically regurgitate this, right? Just say this back very similarly to what we have here. It's the probability of getting a value of a test statistic that is at least as extreme as the one you got, or more extreme, okay, if the null hypothesis is true. So basically what we're going to do is we're going to figure out what's the probability that I would get a sample as far away from the null hypothesis as I got if the null hypothesis is actually true. And if that probability is really small, I'm going to say, you know what? I don't think the null hypothesis is true. Because I know my sampling is good. I did a simple random sample, did everything else right. All my conditions were met. Okay? So that's kind of what we're gonna think there. And then we write a conclusion. And there are two parts to your conclusion. So first thing you're going to do is you're going to say you're going to reject the null hypothesis or you're going to fail to reject it and say why. Either the p-value is less than the significance level or the test statistic falls within outside the critical region. Something along those lines, which we'll get to. And then you state it in the context of the problem. What does it mean when you say I'm rejecting the null? If you say to me, Ms. Burkett, we did this problem, we ran this hypothesis, and we decided to reject the null because the p-value was less than the significance level. I'll be like, okay. And in my mind, I'm like, I'm with you. But if we go to a teacher that doesn't know statistics, which is a lot of the teachers in this building, which would have been me before I taught statistics, and someone said the same thing. Let's say we go to like Mrs. Dell. That'd be fun. No, actually, she knows statistics. So let's go to somebody else. Let's go to Mrs. Partridge, because she definitely doesn't know statistics. We like to give her a hard time. And we said to her, hey, we decided to reject the hoe because the p-value is less than the significance level. She's gonna be like, you did what and why and how? And not really understand it. So this second sentence is going to explain it to her. Second sentence is going to explain it to somebody who doesn't necessarily understand statistics, and also prove that you do understand it. Okay? Okay, so decisions, how do we decide whether to reject or fail to reject? There are two methods, and we're going to talk about both of them, and you're going to have a preference. I suspect I know what your preference is going to be, but to be honest with you, some of you will prefer the other method. I think most of you will probably prefer this one, right here. But I think some of you will prefer the traditional method. In the traditional method, we're going to look at the critical region and see where our test statistic falls. Does it fall in the shaded region or not in the shaded region? If it falls in the shaded region, we're going to reject. If it falls outside of it, we're going to fail to reject. In the p-value method, we're going to take our test statistic, find the probability, and if the probability is less than my alpha level, my significance level, I'm going to reject, and if it's greater than it, I'm going to fail to reject. Yes?
So like on the AP test, they could give you information where you could only make the judgment probably based on one or the other, right?
Well, on the free response, I have never seen one where that's the case. So in free response, you're going to be allowed to decide whichever one you like. But on the multiple choice, there are questions where you have to be able to do,
so you have to know that.
understand
Does it fall in the critical region or not?
Yes, yeah. So there will be, I would say, multiple choice questions where yes, you have to know. But free response, I don't think I'm pretty sure I've never seen one where you have to do a specific method.
Okay.
They would have to say to you, use the p-value method or use the traditional, like they have to very specifically say that to you in order for you to have to do it. But we'll do both. And at the beginning, we do the one that we know how to do best. That's where we start. And then we challenge ourselves. Cool? And on the test, we do the one we're better at. Right? Clear. any tests in my class, any AP tests. So there's the test rubric for the AP exam. This is what they're gonna look for every time. You're gonna, I guarantee, well, say I guarantee, I think last year they did not actually have a hypothesis test on it. But pretty much every year on the AP exam, they have at least one, a lot of times more than one hypothesis test in your free response questions. And this is what they're gonna look for. The hypotheses, the test, the mechanics, and the conclusion. Now I'm gonna tell you what I'm the worst at, so you're gonna have to hold me accountable to this a little bit. Name the test. I'm terrible at remembering to do that. When we state the conditions, we also are supposed to say what test we're running. Okay? Today, we will only know one, so we'll run it every single time. But like in 2 weeks, 3 weeks, 4 weeks, we'll know 15. Maybe 15 is a little bit of an exaggeration, like 5 or 6. So we need to say which one it is. So hypotheses, conditions in naming the test, mechanics, the math behind it, and the conclusion. Okay? That's what they're going to be looking for on the AP exam. So let's do one. Here we go. Ships arrive. We assume for a certain port, 20% of the ships arriving have cargo that's been contaminated. Random sample of 50 ships in the current year include 5 that have contaminated cargo. Does the data suggest that the proportion of ships arriving in the port with contaminated cargoes has decreased in the current year? Okay. All right, so first thing we're gonna do is name the test. So the test we are doing today is the one proportion Z test. It's really important that we use, Z, because eventually, although in this unit it's always Z, we're gonna have other letters in other units, okay? So it's good to get in that habit of it. I always like to name the test first, so that way I'm most likely to do it if I do it first. If I don't do it right away, I might forget to name it. So, let's run our conditions. Always where I like to start. Conditions. What's my first condition?
Random.
Simple random sample. SRS. Let's see. A random selection. So we're good. You see the word random in the problem. So much better than yesterday where we just had to be like, maybe.
Have to assume.
Assume. This time it actually tells us. All right, what's my second condition?
As a n times p, n times 1 minus p.
Yep, but P in this case is my code. It is not my P hats. Okay? So I'm gonna skip that one just for a second. I will come back to it, but I don't know what my ho and ha are yet, so I'm just gonna leave that blank for 1 second. Third condition is what?
10 times 10.
So what's my N?
50 ships.
50. 50 times 10 is 500. That has to be less than what?
Ships in the port.
Number of ships arriving. In U.S. ports. So we'll come back to number 2 here in a second. Let's move on to the ho and ha, then we can go back to number 2. All right, what's my ho?
Less than 20% of ships.
So what's the claim? What I'm testing is, does the proportion of ships arriving in the port, has it decreased in the current year? Right? That's what I'm testing. What was it last year?
20%.
20%. So the ho is always equal to. So P equals 0.2. Always. Always, 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 always. The ho is the equal to part. The ha is what? P is less than 0.2. These numbers, always the same. These letters, always the same. Cool? And then we also have to say, what does P represent?
The proportion of contaminated ships arriving in port.
Proportion of contaminated cargo, ships with contaminated cargo. Of ships with contaminated cargo. All right, so let's go back and finish our conditions, make sure they work. So the P is the hoe. So 50 times 0.2 is what? 10. And 50 times 0.8 is
40.
40. Both of those are at least 10. So that condition is met as well. So notice, I used my hoe and haw. I did not use my p hat. Cool? Questions? So far, so good? All right, next thing I need to do is my test statistic. So, Z equals, this is called our test statistic. Label all the parts for you. Okay, so all of this, no matter if you use the traditional method or the p-value method, are going to be the same. All right, so how do I write my test statistic? What's the equation?
Z equals P hat.
P hat, what is P hat?
0.1.
5 out of 50, right? Which is 0.1. I'm going to write 5 out of 50 just so we remember that that was how we got the 0.1, but that's fine. Minus what? The hoe, 0.2, divided by the square root of, we got 0.2, 0.8, and 50 on the bottom. So all of you, go ahead and try to type that into your calculator. Really easy to have issues with that. So go ahead and do that. All right, what did you get?
-1.768.
All right. Negative 1.7. Okay, I'll just put 7. Is that okay? 768 is fine as well. For those of you that like 3 decimal places. All right, right here, after the test statistic is where I get to make a decision. So we're gonna do both so that you can see both of them. All right, we're gonna start with the p-value method. All right, so the p-value. All right, we have to look at the alternative hypothesis. Less than means what? Which kind of side of my normal curve would be the less than? Left. Very good. So, less than's over here. Shade to the left. That negative 1.77 is here. Find that. Can you find the probability? You can use your calculator, you can use your worksheet. Find the probability of getting a z-value that is less than negative 1.77. 384. Alright, so the probability of p-value would be 0.0384. How does that relate to my alpha level of 0.01?
Greater than.
It is larger than 0.01. So the p-value is, if it's true, that 20% of cargo, that ships that come in to the port, U.S. ports, have a contaminated cargo in it. If it's true, the probability that I get a sample as extreme or more extreme, so a sample of 10% or less, is about 3%, 3.84%. Now, because my alpha level is 0.01, because I have to be, that 1% is my cutoff in this particular case, did I make it to my cutoff? No. So will I fail to reject the null or will I reject the null? I will fail to reject it. So my decision is going to be to fail to reject ho. Have I already desensitized you to that word so quickly? I love it. Because, we have to say why. Because p-value of 0.0384 is less than alpha of 0.01. Or greater than. Oh my goodness gracious. Oh, greater than. Greater than. Does that make sense? Yes? So, if I fail to reject it with the p-value method, I should also have failed to reject it with the traditional method. Let's see what the traditional method would have looked like. Traditional method, let's see, we'll do that. Alright, so the traditional method has to do with the alpha level. What was the alpha level again? 0.01. And the alternative hypothesis was that what? Less than? So I'm going to shade over here. And this is going to represent 0.01 in the shaded region. Can you please tell me what the z-score is that has 0.01 to the left of it? Yep. Negative 2.33. So we label that line as negative 2.33. Are you still with me? Yes? Okay. Now let's draw a line where the test statistic is. So that was in green, so I'm going to go back to green here. The test statistic was negative 1.77. Where would it fall? To the right of negative 2.33 or to the left? To the right, so like right here-ish. Be negative 1.77. This shaded region we call the critical region. Okay? So if the test statistic had been less than negative 2.33 in this case, it had been over here, it would have fallen in the critical region and we would have decided to reject. But because it's in the white area, we're going to fail to reject. Words. Yes? All right, so this case we would say we fail to reject. So because the test statistic that's that negative 1.77 falls outside the critical region. Okay? Are you still with me? Okay? Now, the last thing we have to do is we have to make this sentence make sense. We have to go talk to Miss Partridge. We got to tell her what we came up with. Okay? So we got one more sentence we gotta tell her what we came up with. Let's go back up and see what the claim was. Remind me what the claim was. The proportion is decreased. Do we get to say that that's true? No, we failed to reject the null, that it was equal to 0.2. So we can't say that's not true. So that means we can't say that the alternative is true. If we had rejected this, we could say, we can say this, we got this. But since we failed to reject it, can't say it's not true. So we're gonna say something along these lines. Doesn't have to be worded exactly like this, but it should be something similar.